objective, kenapa nak buat eksperimen ni and so on, method dia, how the method tu please explain in detail lah, because later on your friends are going to do this kind of experiment and I bet your friends result should be differ from yours lah kan. So they are going to do it by their own. So please explain in details about the methodology. And then the last one, explain about how the data should be observed or how the data should be gained, as well as the patterns of the graph and the value itself. Kalau ada untuk value, bagi tahulah berapa range value yang should be dapat. Kalau ada dapat pattern of graph, how the patterns of the graph should be observed and so on. Alright. So we continue with resolving power of prism. So please, if you want to share your screen or your slide presentation and so on, just share your group's punya teamwork lah. Alright, so you may start now.
Okay. Can you hear my voice?
Yes.
Okay. Assalamualaikum warahmatullahi wabarakatuh.
Bagi tahu metik number dulu, siapa yang bercakap ni?
Okay, my name is Nur Humaira binti Muhammad Rozaimi. Metric number 1190951. Okay, we from group 1 will present the first experiment, which is under topic resolving power of prism. So first, we start with theory. The aim of this experiment is to find the resolving power of prism, and the apparatus needed is a spectrometer, prism clamp, mercury vapor lamp, and lens. We will go through the apparatus during simulation. Then the principle: if a spectrograph can just resolve two lines near wavelength lambda with a separation of delta lambda, the resolving power is defined as lambda over delta lambda. To be clear, function of spectrograph is to split or disperse the light from an object into its component wavelength so that it can be recorded and analyzed. It is basically an instrument that separates incoming light by its wavelength or frequency and record the resulting spectrum in some kind of multi-channel detector. Then prism spectroscopy. Newton demonstrated in the 1600s that white light passing through a prism could be separated into its different colors, while at that time he believed in the corpuscular theory of light. We know that these individual colors represent different wavelengths or frequencies. From our introduction to refraction, it is to be expected that light of different colors will bend through different angles. Perhaps the simple form of astronomical spectroscopy is the objective prism. Unsurprisingly, this is a very thin prism that sits in front of telescope objective, often in front of corrector plate of Schmidt's telescope, which is to set wide field result. The resolving power of a prism is given by R equal to lambda over delta lambda, where lambda is the wavelength resolved from the wavelength lambda plus delta lambda. Refraction is due to change in speed of light while passing through the medium, and it is given by Snell's law, which is we know sin I over sin R equal to N2 over N1. From what I understand and from this experiment, we could know the light can spread different colors through prism, and that different color is diffraction grating that has different wavelength. Next, we move to procedure.
Okay, my name is Nur Syadatul Syahira binti Syahrum, matric number 1190962. Then we will proceed to the next part. First, I will introduce the spectrometer first. The spectrometer. Okay, this is the diagram of the spectrometer. This is the telescope and the focusing telescope. This is the eyepiece where we will see the slit through it. This is the collimator, the vernier table, the prism table, and the mercury lamp. This is the vernier 1 and the vernier 2 where we will took reading from it. So we will move on to the control. This is for us to switch on the mercury lamp. For this panel, it is focus on the slit, which is this slider is to focus the slit, and this is for the slit width. You can adjust it to the best focus, and this is to place the prism here. For this change angle panel, it is used to move the telescope, or you also can just drag the telescope like this. And this is to rotate the vernier table. And for this fine angle, it is used for us to fine adjust the telescope. If we are going to move it just for a little, we can use this fine angle like this. And so that's it works the same for the vernier table fine angle. It can be used to move to fine angle for the vernier table. So we will proceed to the adjustment for this experiment. So first we have to focus the telescope from the distance object on a distant object like this. So when we get the focus image, we can press the start button. Then we can switch on the light. Then we can move on to focus the slit. Some tips here. You can move the slit. You can shift away the slit from the cross wire so that we can have a best slit here. So we can adjust much better without the cross wire and the slit width like this. So next, we have to coincide the slit to the cross wire by removing the telescope. This until we can reach the cross wire. You can use the fine angle to get a more focus on the cross wire. Then we move on to the least count of the spectrometer. The formula for the least count spectrometer is the value of the main scale division, the upper one, divided by the vernier scale division. For this spectrometer scale, the main scale has 10 division, which is you can see here 1, 2, 3, and here 10. And the one main scale here cover 1/2 degree, which is equal to 30 minutes. We can press the calculator. And for the vernier scale, we have 30 division here. So that our least count will become 30 minutes divided by 30. And we will get 1/60 degree. 1/60 degree is equals to 1 minute. So the least count we will apply during the final reading, where the main scale plus the vernier scale times the least count, which is 1 minute that we obtain here. So that's all from me.
Okay, my name is Atila Shahida binti Saifuddin, number metric number 1190959. Okay, next we will want to determine the angle of minimum deviation. Simulator. Okay. Okay, first, follow the control as Shahida said earlier, and then in order to determine the angle of minimum deviation, rotate the prism table until we get to see the reflected light through the prism. Okay, rotate the prism table until we get to see the reflected light through the prism. Okay. Okay. So make the slit coincide with telescope cross wire. Okay. Okay. Next, slowly rotate the vernier table by using vernier fine adjusting slider until we get to see the slit is stationary for some moment. Okay. Okay, note and we note the reading on the scale. And then remove the prism from the prism table. Okay. Turn the telescope parallel to the collimator and note the direct ray readings. Okay, in order to find the angle of minimum deviation, we need to find the difference between the direct ray readings and the deviated readings. Okay. Okay, that's all.
Bismillahirrahmanirrahim. My name is Siti Aisyah Anisha binti Kamaluddin, matrix number 1190955, and I'm going to explain to determine the resolving power of a prism. Okay, firstly, rotate the vernier table here. After we place the prism, we rotate the vernier table so as to fall the light from the collimator to one face of the prism. One face of the prism and emerge through another face. So we move the prism. Move the prism. Okay, then we also can move the telescope to find each color of different rays, each ray colors. So to find the different color, emerge rays of different color. Okay, here we find it. I'm going to focus it a little bit. It's not sharp. Okay, and then we remove the prism and note the direct ray reading. Direct ray readings, here we remove. We turn the telescope to parallel to get the direct readings, and so we measure the readings, and then after that we place again the prism. We find the minimum angle of minimum deviation for different colors. So we move back again the telescope so we got the different color here. Okay. So how to find the angle of minimum deviation? As for me, after I turn this telescope here, we slightly turn using fine angle. We slightly turn the vernier table, and then we can see here that the rays turn to move to the right and then stay at the stationary moment, and then they turn back to left. So that is where the minimum deviation starts. When they start to turn to left, that is the minimum deviation angle. So we turn back again before this is the stationary moment. So we are going to get the reading of minimum deviation, and then we move the telescope to get the different rays, the color that we want, to the cross wire. Then we are read the readings of the spectrometer, and then after that we find the refractive index for this color using equation. This is the equation to get the refractive index for lines, the colors that we choose. And then resolving power, this is example resolving power for yellow and blue. We have got these experiments. We also want to find the resolving power using this equation. For example, using yellow and blue, so we get the resolving power where N and B and Y are the refractive index of blue and yellow, and this N and B plus NY over 2 is called average for refractive index. Okay, that's all from me. I'm going to pass to my friends. Thank you.
Okay, next.
My name is Siti Aisyana binti Ahmad Rizal. Metric number 1190953. Can you see the screen?
No.
Oh, sekejap. For the table, the line is the color that you want to read the reading, and for refractory readings, we've got from the procedure, and for V1 and V2 for each color. Direct readings, we've got where when we remove the prism, and the direct readings for V1 and V2 for all color is constant. For difference, minimum deviation, we've got from dividing minus refracted ray with direct readings. For mean, I'm using this formula. Delta M multiply with lambda. Delta M is the minimum deviation. For refractive index, we use the equation 3. Refractive index for the line of the color that you choose, N1, and the refractive index is also the same for N2. To find the average of refractive index by using this formula, N1 plus N2 divided by 2. For resolving power for the color for N1 and N2, we've got the formula omega is equal to N2 minus N1 divided by N minus 1. For the result, angle of the prism is constant, 60 degrees. Angle of minimum deviation of the prism, we can get from the procedure. For the refractive index of the material of the prism, we can calculate it using equation 3. And for dispersive power of the prism, what I have found, the formula is the same as resolving power. This equation. So that's all from me. Thank you.
Done. Group 1 done with your presentation?
Yes, we are done, doctor.
Okay. then all the results should be obtained. Is there any expectation of graph or just the value only from this experiment?
Just the value only, no
Just
graph.
the value, no graph.
No graph. All right. Okay, so mana tadi gambar tadi? All right, so thank you, Group 1. It's a very nice presentation, clear and detailed. So, any questions from the other group?
I'm sorry, doctor, but is our explanation is correct for our reading for table?
Sorry, reading for table.
Yes.
Potong table tadi tak nampak tadi ni.
Shano boleh share. Share screen.
Based on your methodology and your explanation and step by step, so when you are placing the value the equation, and then you will get the value of n, which is the objective of the experiment. So for me, it's okay.
Is our explanation for mean is correct also?
Mean from difference minimum deviation apa tadi?
Yes,
Time
minimum deviations times with wavelength for line. Each line color wavelength. Is it correct?
Macam mana dapat how you get that equation?
We are just briefly surfing on internet searching, and I think so using that formula.
Value n dapat berapa bila guna that mean equation?
Bila guna tu dapat dia punya nilai dia darab dengan 10 negatif 5.
N biasa
And dia setiap line tu dia beza sikit je. Kalau misal kata kalau violet tu 1.720. Betul ke, doktor?
tak, violet 1.7
20.
Merah
Merah saya tak ambil, saya ambil yellow.
tak kira semua ke?
Tak, dia apa tu? Saya kira 4 saja.
4 saja. Kenapa tak kira each of the colours appear tu?
Kami guna daripada for procedure. Yang procedure tu dia nak 4 je. Jadi saya kira.
Kalau you nak justify whether it is right or wrong, you kena tengok lah kalau basically, okay. Before that, ada question tak from the other members of group yang lain, ada soalan tak? Because you are going to tak ada. Faham
InsyaAllah.
InsyaAllah. Okay. Okay, so tadi group 1 G1. Alright, so I have question for you. So this is a resolving power of prism. So basically you learn that when we shine the white light, then it will deviate or disperse into some kind of colors kan. So my question, why we are able to see all the colors? Guys, group G1?
Yes, doktor?
Why we, in this experiment, why you guys are able to see the colors deviate from the white light?
From the white line. Meaning that due to the prism dengan angle.
Kenapa you nampak color merah, hijau, biru, green semua tu? Kenapa nampak?
The reflected light from the source to telescope.
Source apa? Color apa source tu?
Putih, white.
Color putih. Okay kan? Alright. So soalan saya, kenapa you boleh nampak yang colour lain-lain after disperse tu? You boleh nampak biru, hijau, kuning kan? Violet kan? Okay, why? Basic question je ni. Sebab
Sebab prism tu ke?
Sebab dia punya refractive index ke?
okay, sikit lagi. Dalam optik belajar kan kenapa kita boleh nampak all those colour? And there has some colours yang can enhance. Because all those colours, cepat Jiwan.
Visible light.
Yes.
Visible.
Right. We have wide range kan? Alright, so only our eyes can see in the range of the visible. Alright, so at what wavelength of that visible light? Jiwan? Aisyah aja jawab yang lain. Cepat. Wavelength for visible, the range of the visible light that our eyes can observe.
And 380 until 750 nanometer.
Alright, so between 300 to 700 lah kan. So less than or greater that range, we need some technology lah macam let's say infrared, kita tak boleh nampak let's say we have laser light in infrared, they have the illumination of the beam. Tapi kita tak nampak pun dia punya aluran beam tersebut. We need some kind of technology, let's say detector to see the light because it is out of our range. Okay, so based on your question previously, so if you want to justify either your answer, the value of n is correct or not, so please take note what what color is the longest and what color is the shortest and its relationship to the the index biasan itu. So kalau you jumpa nanti, let's say kalau you kata merah itu paling pendek wavelength and violet tu paling panjang wavelength, so macam mana dengan dia punya nilai n dia? So should be bila you dapat variation daripada situ, then your answer is correct lah. Boleh? Boleh Jiwan?
Boleh. Untuk yang min pula doktor, untuk dapatkan apa? Untuk min.
Min tu okey lah tu saya rasa because you serve macam tu kan. Sorry
Jadi untuk kita mencari min tu untuk apa doktor?
Untuk cari min tu tak apa, bukan guna untuk cari n ke? Ada delta wavelength tu.
Kami guna equation untuk n guna daripada equation yang diberi dalam procedure je.
Apa, cuba kira dulu. Maksudnya you kena kira semua color dulu lah.
Ya.
Nanti bagi tahu saya nilai n tu macam mana variation dia. Is it dia increasing ke, decreasing ke, so nanti barulah you boleh justify your answer n tu betul ke tak.
Saya ambil yang yellow, saya dapat 1.728. Meanwhile, violet is 1.720. So it is increasing.
Ambil ni lah, longest and shorter one.
Okay.
Alright.
Thank you, doctor.
So before that, one more question for group 1. Okay, so since this is the simulation, okay, so when you are entering the real lab session in USIM, so what is since you are dealing with the telescope, prism and the source of light, and then you are going to observe the dispersions of colors from the white light. So what is the most crucial step before you did the experiment?
The surrounding must be dark.
Ada yang dah tahu jawapan ni.
I know. It remind me of experiment during semester 1.
Alright, okay. So thank you Syadato. Yes, correct. So for your information, later on, if you are entering any photonics lab, and you are dealing with the laser or the optical fiber ke apa ke anything, so first thing first, you need to make sure your setup itself or the surrounding must be in the black punya surround lah, or at least dia tak semestinya black, but at least there's no light from the outside, then because the outside light may mengganggu you punya setup because this is the optics. So speaking of optics, this is all about light. So biasanya, and then biasanya speaking of optic experiment pun, kalau let's say you do the experiment today, then you need to finish it today, because when you do it tomorrow or the other day, I bet you the results will not be the same as today, because the first one setup dia dah berubah, because you ganggukan setup, because optics is dealing with mirrors, with lasers light, with optical fiber and so on. So setup itu we are dealing with a very tiny devices. So dia punya setup tu mudah terganggu. Alright, so itu antara precaution step lah tu. This is differ kalau you go to the microelectronic punya lab. Microelectronic you dealing dengan soldering apa semua, apa high power voltage kan. So you buat hari ni pun esok dapat voltage yang sama juga. So dia tak kisah. Tapi bila optics punya lab, this kena take some precaution step lah. Okay, so thank you for group 1. So hopefully group lain tu okay lah. So nanti you guys kena buat ni. Okay, so we are moving to the next group 2. Rasanya dah cukup kot member. Group 2 which is about group 2 apa? Spectrometer dispersive power of prism ke?
Refractive Index betul.
Alright, so you may start lah group 2. Group 2 ada tak? Blank dia tu? Okay, ada dah. Alright.
Hello, Assalamualaikum.
Salam.
Can you see my screen?
Yes.
Okay, thank you. Okay, so our group 2 will be presenting about the lab optics about spectrometer, refractive index of the material of a prism. So the aim is to determine the refractive index of the material of a prism.
So we go to the apparatus. Alright, apparatus is spectrometer. Alright, a spectrometer is any instrument used to probe a property of light as a function of its portion of the electromagnetic spectrum, typically its wavelength, frequency, or energy. Next, prism clamp, sodium vapor lamp. A sodium vapor lamp is a gas discharge lamp that uses sodium in an excited state to produce light at a characteristic wavelength near 589 nanometer. And the last one is lens. So we proceed to the principle.
My name is Muhammad Nilihi bin Muhammad Yusof. My matrix number 1190952. So for the principle for this experiment, when a beam of light strikes on the surface of transparent material, for example glass, water, or quartz crystal, the portion of the light is transmitted and the another portion is reflected. The transmitted light ray has small deviation of the path from the incident angle. This is called as refraction. So refraction is due to the change in speed of light while passing through the medium. You can see from the Snell's law, sine incident angle over sine refractive angle equal to refractive index of the second phase over refractive index of the first phase. And next, the speed of light on both phase is related to the equation C1 over C2 equal to N2 over N1. So C1 is the velocity of wave in first phase, while C2 is the velocity of wave in second phase. Akmal, can you move the slide? Okay. So as you can see, if nampak. If refract, oh, Rajah tak terang.
Oh ha.
So if refractive index of incident angle less than refractive index of if N1 less than N2, that means the angle I more than the angle than R. So the light will move close to the normal to the plane. But if N1 equal to N2, so the angle for I and R is equal. And then if N1 more than N2, the angle for I less than angle for R. So that's all from me.
All right, so next we move to the refractive index of the material of prism. All right, the refractive index of the material of the prism can be calculated by the equations n equal to sine bracket a plus d divided by 2 per sine a divided by 2, where d is the angle of minimum deviation. D is different of different colors. So if the question asks to us to find the refractive index of the material of the prism, we just use this formula and substitute all the value that are given by the questions, and we just calculate the value and we got what we want. Okay. Next.
Okay, next is the procedure. Okay, first you need to dah nampak ke belum? Dah.
Nampak.
untuk prosedur dia, first kita buat fokus dulu kepada teleskop to find the clearer image, and then press start and switch on the light. Okay, and then place the prism. When we place the prism, we need to move the telescope to this side and both sides to find the line, this one. Okay. Okay. And then after we got the coincide, we record the reading when the 1 and when the 2. After we record the reading, we move to next phase, opposite phase, and do the same. We get coincide and we record the measurement reading. That's all from me.
Dah nampak? Okay, my name is Muhammad Aiman Hakim Muhammad Temiran, metric number 1190965. I will explain of the procedure to determine the angle of minimum deviation. First, rotate the vernier table so as to fold the light from the collimator to one face of the prism and emerge through another face. Refer the given figure. We open the simulator and we adjust the focus the telescope to obtain the image. And we press the start and switch on the light. We use the sodium vapor lamp, so we get the yellow light. And then we adjust the slit focus to get a better views of slit. And then we place the prism to get the refracted ray. As the procedure say, we need to refer the given figure. So we move the vernier table like this. Okay, then we move the telescope to get the slit coincide with the crosswire. Jauh. We can also use the fine angle to get the better angle. And then we record the vernier table, record the readings of vernier 1 and vernier 2. After we record the vernier 1 and vernier 2, we remove the prism to get the direct ray of the collimator to the telescope. So we move the telescope to get the direct ray from the collimator. And then we record the readings of vernier 1 and vernier 2 also. That's all from me. we proceed to the next.
Okay, can you see my screen? Hello?
Yes.
Oh, okay. Okay, the next is results. So we want to find sekejap, we want there are three things that we need to find, which is first is angle of the prism, and second one is angle of minimum deviation of the prism, and last is the refractive index of the material of the prism. So there are two tables of results that we supposed to get. First is for angle of prisms, and the second one is for minimum angle of deviation. So in this result, there are three parts, which is main scale reading, vernier scale reading, and total reading. And into, so we calculate, we observe that by doing experiment just now, and then we record the data, and then we find the difference between A and B to find the minimum the angle of prism, which is the mean. So next is for the minimum angle of deviation. Also, we have the mean scale reading, vernier scale reading, and also total reading. For phase A is when just like earlier, Aiman moved the vernier table to make the base of the prism parallel to the light source, which is sodium lamp. And then phase 2 is when he removed the prism and he calculate the direct light ray of the sodium lamp. And then we observe and we record it, and then we find the difference between the phase 1 and 2, and then we do calculation. So first is for angle of prism. The calculation is to find the mean is 2a equals to the difference that we get from vernier 1 and vernier 2. We plus both of it, and then we divide it by 2, and then we get the angle of prism. This is our result, 120.25 degrees. And then for the second table, we do the same thing. We find the mean between vernier 1 and vernier 2 total reading, and then we get 192.97 degree. And then for the refractive index, there's an equation that is there is told before by Farhan, which is sine A plus D over 2 divided by sine A over 2, and then we just replace A and D. A is 120.25 degrees, and then D we replace with 192.97 degree, and then N, the refractive index of the prism, we will get 1.46. 1.46. Okay, that's all from our group. Thank you very much for listening.
Sekejap, siapa yang Akmal tunjuk tadi?
Huh?
Tunjuk tadi, tag result tadi. Okay, so basically you guys objective first one find the refractive index Okay.
Angle prism.
Cari apa lagi? Cari apa?
Minimum deviation.
Minimum deviation. Okay, and dua tu je. Guys. cari dua tu je ke?
Refractive Index.
Refractive index, alright. So refractive index, alright. So based on your results, so refractive index of the prisms you got is 1.46. Alright. So have you checked that is the value, the general value for all the prism outside? Dah check ke?
Oh, tak.
Kena check jugalah. First thing first, you kena tahu the prism is what kind of material kan. So nanti kalau later on you nak check, tengoklah let's say kita guna material yang general je lah. Tak adalah sampai material yang susah kan. Biasanya prism dia buat daripada apa and then you check lah kalau you got that kind of range let's say between 2 then your answer will be correct. Alright, and then the second one, maybe group 1 boleh tengok kot because group 2 ni dia buat mean based on the mathematical kan, nak cari mean plus and then divide by 2 kan. Saya tak cakap lah group 1 punya method of finding the means false, sebabnya maybe you cari kat internet tu that equation have been simplified or that equation have been summarized or have been derived so that's why lah tadi group 1 saya suruh you check dulu, but then nanti you boleh tengok jugalah kot cara group tu buat, maybe dia guna mathematical punya mean saja, very simple, plus and divide by 2 so tengok nanti baru you boleh kira you punya n. Alright.
I'm sorry doktor. Kami pun fikirkan nak guna juga formula ni.
Okay.
Tapi dia nak mean tu vernier 1, vernier 1, vernier 2, vernier 2.
Okay, and then?
Dia bukan nak macam ni. Macam contoh yang ni kan boleh tambahkan dua-dua kan, vernier. Dua-dua vernier bahagi 2. Jadi kalau nak guna formula ni nanti kan akan dapat satu nilai je kan. Tapi based on table, dia tu different vernier tu different means. Jadi kami pun tak tahu macam mana nak buat.
Tak sama je ke?
Lain jadual.
Lain jadual, maksudnya you guys punya tadi mean ada 2 ke?
Mean dia ada 2.
From scale yang besar dengan scale yang fine scale
Bukan, maksudnya main scale dengan vernier scale memang dah gabung kan. Jadi tu ialah vernier 1. Vernier 1 punya mean apa, lepas tu vernier 2 punya mean apa, macam tu.
Group ni satu guna vernier 1 saja ke group 2? Group 2 hilang dah?
Vernier 1 dengan vernier 2 kami tambah terus.
Nampak kami tambah terus Akmal kata. Apa nanti G1 boleh terus group 1 nanti try dulu tengok how's the reading Okay. So saya tengok group ni senang saja cari refractive index, cari RI saja. So but later on in your discussion please discuss how difference yours and with the real prism outside So kalau you dapat, saya rasa kalau you dapat below maybe 2 tu okey lagi lah, janganlah sampai metal punya kan sampai 10 ke 15 ke, so it doesn't make sense lah. Alright, so ada soalan tak daripada group 1 dan group 3 because you are going to do this one later on and I bet nanti you punya reading pun akan slightly different. Kalau sama tu maksudnya you are copying group 2 punya result
Doktor. Nak tanya doktor, possible tak kalau refractive index satu material tu the below than 1?
Below dia depends on material Akmal. Siapa tanya tu? Farhan?
Yes.
Depends on material. Possible saja. Depends on material lah. Sebab tu saya kata you kena check dulu prism tu nanti nak check dalam discussion, nak buat discussion material apa baru you boleh buat banding beza. Janganlah you pergi buat satu material yang satu let's say you compare ceramic dengan kaca ke. No lah. Mesti material yang sama lah.
Okay. Thank you doktor.
Alright. Soalan daripada grup lain okey ke? Senyap dah tu, all is well lah tu.
Okay.
Alright. Okay, so thank you. Oh sorry, one last question for group 2. could you please give me anything surround you, the applications of the prism?
Telescope, periscope.
Periscope
Got lagi?
phone screen.
Sorry?
Phone screen.
Phone screen. Okay, saya berminat dengan phone screen tu. How that prism acts in how the concept of the prism acts in your phone screen.
Oh, dia ada private apa dia dipanggil private screen protector. Maksudnya dia boleh ditengok pada angle yang 90 sampai 80 je. Kalau kita tengok dari tepi memang tak nampak lah.
Oh, maksudnya the image dah tak clear lah.
Tak clear.
Tak clear. Alright. Thank you group 2. Aku mau orang Kedah ke Akmal? Mau orang Kedah ke?
Orang Kedah.
Okay.
Parit buntak.
Alright, thank you.
Parit buntak.
Parit buntak. Oh, okay. Patutlah tak lari slang dia. Okay. Thank you group 2. So, hopefully G1 dengan G3 faham nanti you nak buat. Okay, so we move to the last group 3, which is group 3 tentang apa Diffraction grating ke?
Diffraction grating.
Alright, you may start. You may start your presentation.
Hello, nampak tak? Assalamualaikum.
Nampak.
Okay, terima kasih.
Alright. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
My name is Nurfara Auni, Binti Muhammad Kamal Rasmadi, metric number 1190968. Okay, so our experiment is about diffraction grating. Right, so the aims are to determine the number of lines per millimeter of the grating using the green line of the mercury spectrum, and to calculate the wavelength of the other prominent lines of mercury by normal incident method. Apparatus is spectrometer, diffraction grating element, and also mercury vapor lamp. So why we use mercury vapor lamp? Because atoms in dilute gas of the vapor lamp, when it radiates light, the light can be seen through diffraction grating as line spectrum, which is made up of bright lines of color. Okay, so the theory is when a wave train strikes an obstacle, the light ray will bend at the corners and edge of it, which causes the spreading of light wave into the geometrical shadow of the obstacle. So this is called as diffraction. So basically, as we know, light is always traveling at straight line. However, when the light wave passes a near barrier or obstacle, they tend to bend around the barrier and spread out. So a diffraction of line occurs when light wave passes by a corner or through an opening or slit that is smaller than light wavelength. Alright, so next one about the single slit diffraction. When wave passes through a gap, which is about as wide as the wavelength, they spread out into the region beyond the gap. Huygens principle. Huygens consider each point along a wavefront to be the source of secondary disturbance that forms a semicircular wavelet. So the superposition of secondary wavelets that will produce a diffraction. So when the secondary wavelets spread out and overlap each other, interfering with each other to form a pattern of maximum and minimum intensity. The pattern formed on screen consists of a broad central band of light with dark bands on either side. The dark bands are caused when the light from the top half of the slit distractively interferes with the light from the bottom half. Okay, we consider a slit of width A. Okay, the angle, the path different between the top and the bottom of slit is a wavelength. So when I'm talking about the dark band here, the destructive interference occur because the path difference between the top and the middle of the slit is half of the wavelength. At this angle, all the light from the top half of the slit will get cancelled with the light from the bottom half to produce the dark band. Okay. The formula here, intensity minima will occur if this path length difference is an integer number of wavelength. This A times sine theta equal to n lambda, which is n is the order of each minimum, lambda is the wavelength. Scroll down. Okay, the formula is of intensity in equation in the equation 3. Total phase angle can also be called as division angle. And then maximum intensity. Lambda is the wavelength of the light. So at normal incidence, when we look at equation number 5, sine theta equal to n, which is number of lines per unit length of the grating, times with the order of spectrum and the wavelength of light. And okay, look at the picture below. The diffraction, when we look at here, diffraction means it will produce different angle, different directions of the diffractive ray. Alright, that's all from me. Thank you.
Assalamualaikum and good morning. My name is Siti Nur Isyirah Farahim binti Muhammad Said with metric number 1190967. I will present about procedure for real lab. Before I go into procedure in real lab, I will present a little on the precautions taken that might be useful in the future. The first precaution is optical systems are sensitive and are often fine-tuned. Be very careful with the equipment as a slight nudge might damage the equipment. Secondly, the diffraction grating is a delicate component. Do not scratch the surface or touch it with your fingers. The whole procedure may be divided into 3 parts, which is the first one, adjustment of the spectrometer, secondly, adjustment of the grating, and lastly, the actual experiment procedure. Since the procedure for your lab in VLab website is a little bit too long, I will try to shorten it. So with calibration, the first step is align the collimator and the telescope so that the vertical crosshairs, which is seen through the telescope, are aligned with the slit, which is seen through the collimator. Second, loosen the spectrometer table lock screw. Align the vernier scale on the spectrometer table so that it is collinear with the optical axis of the telescope and collimator. Tighten the lock screw. Lastly, use the spectrometer table fine adjust knob to make sure that they are perfectly collinear. The actual experiment procedure, we start with since the telescope is already calibrated, the telescope is then released and is brought to observe the direct image. On the either side of the direct image, the diffraction spectra are seen. The telescope is turned slowly towards the left so that the vertical cross wire coincides with the violet lines of the first order. The readings of the vernier are taken. The vertical cross wire is then made to coincide with the other lines on the left, and the vernier readings are taken in each case. The telescope is then moved to the right, and the reading of different lines is similarly taken. The difference between the readings on the left and right of the same vernier is determined for each line. The mean value of this difference gives 2 theta twice the angle of diffraction. Thus, the angle of diffraction theta for each spectral line is determined. The wavelength of the green line is 546.1 epsilon negative 9 meter, while the number of lines per meter, which is the symbol is n, of the grating is calculated. Using this value of n, the wavelength of the other prominent lines in the spectrum are calculated. That's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Normaisara Batrisha binti Muhammad Baharudin Buhari. My matrix number is 1190966. Next, we go to the simulator. Okay. Okay. Can you see the simulator?
Yes.
Okay. Okay, this is the simulator for diffraction grating experiment. First thing first, we must need to do for this experiment is we have to focus the telescope so that the object become clearer. Like this. And then when the object is clear, we can start the experiment. Okay, then first we have to switch on the light. We will see a line here, a white line here. And we must focus the slit width for the slit, for the line. The line must be narrow, clear and fine so it can, the result we observe will be accurate. Next, adjust the telescope so that the slit will at the center, the vertical line here. Then we can place our grating here. This is our grating. Then we have to do the normal incidence method. First, rotate the telescope. This is telescope towards your left hand side or right hand side. With 90-degree angle. But I will do at the right hand side first. We must observe that here will turn to 90 degree and 270 degree. Here we will get here 90 degree and then vernier 1 we will get 270. And then now we rotate the grating table towards the telescope up to 45 degree. Here grating table we change it up to 45 degree. See, okay, here. Until we get like this. Next, rearrange the telescope so that it will be 0 degree and 180 for the both vernier table. And to make it accurate. Ta-da! And then we get here. Then set the vernier table back 45 degree, but must opposite the direction from the previous. So it will be negative 45 degree lah. Like this. And then we get the real and then we can continue our experiment. Okay, next we can start to observe the spectrum. Choose whether we want to observe from the left or right hand side. Focusing the telescope to the green color, we move the telescope to the green color. Here, I move the telescope to the left hand side. Okay, here we get the green color. Then we can observe the vernier scale at the vernier 1 and vernier 2. So our aim first is we would like to know the grading element of green color, and then after we know the grading element of green color, we can continue to calculate at our result table after that. Next, after we get the left hand side of green color, then we move the telescope to the right hand side. This. The right hand side. Okay, now we can observe the spectrum green light at the right hand side, and you guys can take the scale vernier 1 and vernier 2. Next, after that, there will be more color after that, like yellow, blue, green, violet 1 and violet 2. So after that, we continue as the next step, like we do for the green color, to observe the green color. So that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Alia binti Abdul Latif. Nombor metrik 1192652. Can you guys hear me?
Yes.
Yeah.
Okay. So, from the adjustment and or the experiment that we have done early just now, we can might please show the yes. Okay. So for the green first, our aim is to get the end of the green color, so we can standardize the grating element for other color, such as yellow, blue, green, violet 1 and violet 2. So for vernier 1, on the left, just now we get it is 40 degree, and when you went for right side, we get 18 degree. Okay, so then for vernier 2 left, we got 160 degree, and for vernier 2, 198 degree. Okay, so you guys can just plug in the wavelength, the angle, and in the automated jadwal, in this jadwal, and then we can get the end, and then we can just copy the end of the green color and put in the in this grating element. But the color, we can change it to the color that we want to know the wavelength. Such as, okay, for now, yellow. Okay, so then you guys can just repeat the experiment like my Sarah do just now to get the vernier 1 left and right angle, and then vernier 2 left and right angle, and then lastly when you guys plug in the angle, the wavelength will be automated. Wavelength for yellow color, as example, will be appear here. Okay, but how can we, but what is the formula for the to find wavelength and the end of the green line? So we can go to the procedure. Okay. Okay, here we can for the lab report, you guys can plug in all the angle that you guys get from the experiment just now, and then for the difference reading to theta, you guys can for vernier 1, you guys can just add the amount of vernier 1 for left and vernier 1 for right, and that is the difference reading for vernier 1, because in diffraction grating we have two sides of left side and right side. So the total will be, the total from the center slit will be theta and theta. So when we add those two, we will get 2 theta. And then from the mean, you guys can just, okay, before that, for difference reading for vernier 2, you guys can just add, just like before, vernier 2 left and vernier 2 right, and then the total from difference reading, you guys can add and divide by 2, and that is our mean. And then for the end of the green line, you guys can just put in the mean value, sign theta, theta is mean, and divide by n, number of order, which is 1, and times the wavelength of green light, which is 546.1 nanometer. Okay. For the determination of wavelength for prominent lines, in the experiment that we do, we just get yellow 1, we just see yellow 1, blue-green, violet 1, and violet 2. So we cannot see, for us, we can't see the yellow 2 color, yellow 2 line. So we plug in for just same as the green color, the green line, we fill in the whole schedule, and then the difference reading and the mean is also the same as the green line, and to calculate the wavelength of each color line, sine theta, theta is mean, over n, and is order, which is 1, and the n, the standardized n, from, we use n from the green line. Okay. Okay, then when you guys calculate, you guys will get the all wavelength of yellow, blue-green, violet 1, and violet 2. And then if for a comparison, you guys can just search on the internet for the theoret the theoretical the actual spectral lines of mercury. For as example, violet 1, violet 2 has in actual it has a wavelength of 404.6 nanometer. So you guys can just compare with the result that you guys get to know whether the different percentage of the theoretical and the actual values. I think that's all from me. Thank you.
Done your presentation, group 3?
Yes, Doctor.
Alright. So basically your objective is apa tadi?
To determine the number
of lines
rating using green line of mercury spectrum, the N of green line. And then second, to calculate the wavelength of other prominent lines of mercury by normal incidence method. The other
Alright. Okay. So clear tak group the members of group 1 and group 2? You are going to do that. Clear. Boleh buat ke tu?
Masya-Allah.
Oh, for me it's quite a long explanation daripada Alia tadi kan. Panjang lebar dia terangkan. So group 2 okay. Is it okay for you? Senyap je tu. Hilang dah members of group 2. Group jejaka ni.
Okey, Doktor.
Okay.
Boleh.
Boleh, tak ada soalan
Tak ada.
Alright. Okay, so basically slightly different from group 1 and group 2. So group 3 is about the phenomenon of diffraction. This is diffraction grating. Okay, so a few questions for you, group 3. So in optics, you learn that we have two types of diffractions. So could you please name it the two type of the diffraction? Pada jenis-jenis diffraction, we have two types. Group 3, apa dia?
Fresnel tu ke Doktor?
Fresnel diffraction, and then the other one is?
Fresnel diffraction. Fraunhofer.
Fraunhofer. Okay, so in this experiment, which one punya diffraction? Fresnel ke Fraunhofer? Group 3.
Fresnel.
Alright. So in this kind of experiment, you are using the Fresnel diffraction types. Okay. And the question is, what is the difference between the diffraction and the interference? Because sama je kan, you are going use slit and then that light, the source of light will diffract and so on. So what is the difference between interference and diffraction? Guys, dalam kelas belajar kan dengan doktor aku kan? Apa problem? Apa dia Insyirah?
Diffraction occurs when wave encounter an obstacle, while interference occurs when two waves meet each other.
How about the sources?
diffraction has only one sources from the same wavefront, and for interference, it is from two separate wavefront. The interaction.
Okay, alright. So betul So both correct. Alright, one more last question. Could you guys please give me the example of the diffraction of diffraction of sound. Sound is part of a wave, kan? You guys learn in optic that sound is also a wave. So could you please give me the example of the sound diffraction? Group 3.
Doktor, the contrast in sound from a close lightning strike and a distant one.
Itu. Then apa yang berlaku? Apa?
The thunder from a close bolt of lightning will be experienced as a sharp crack, indicating the presence of a lot of high frequency sound.
Okay, baca skema jawapan ke tu?
Tak adalah. Sikit.
Right. Okay, so itu adalah example of sound apa kejadian apa? Lightning apa? Guruh peti.
Thunder.
Alright. Okay, okay, one last lagi. Mungkin dia tahu aku ada bagi tahu kot. This diffraction experiment is falls under classical physics or modern physics? Senang je soalan ni. Kena tahu ni. You guys could be able to differentiate what experiment in classical physics, what experiment in the modern physics. We have a lot of experiment like interference, diffraction, photoelectric effect, young double slit experiment. So because this is the optic subject kan. So you maybe saya tak sure dah belajar belum all about the wave particle duality and so on. So in order to differentiate or to understand deeper about the wave particle duality, you should be able to analyze all those experiments. So my question is, this kind of diffractions falls under classical or modern physics?
Modern physics.
Diffraction, sure.
Diffraction grating.
Alia cakap lain. Apa ni, tak ada kesefahaman ni grup 3 ni. Classical or modern? Oni?
Classical.
Classical, sure?
Yes.
Kenapa awak kata classical? Apa dia? Cepat yang paling simple sekali. Kenapa dia falls under classical? Sebab apa? Hilang dah grup 3. Grup 3 masih ada lagi tak, cepat last. Sebab
tak tahu dah.
Tak ada ni ke? Tak ada discussion dalam optik ke? Mesti dah belajar kan diffraction kan? Sebab apa? Cepat. Ni ada markah ni soalan-soalan ni. Apa cepat? Diffraction. In this kind of diffraction, it is all about apa?
Light.
Wave.
Betul. Okay, apa dia tadi? Apa dia?
Light wave.
Light wave.
Light wave.
It is all about wave, right?
Wave.
Gelombang. So speaking of waves, so it is under Classical.
Classical.
So bila you have, let's say, photoelectric effect dah belajar belum? Guys, photoelectric effect. Dah belajar kan? Dah pernah dengar kan? You have cathode, you have anode, and then you have some metal, and then you have light. When the light shines on the metals, it will extract some kind of photoelectrons kan? Remember photoelectric kan?
Yes.
So that photoelectric tu, it is all about the particle because we are discussing about the electrons, the photoelectrons, kan? So that's why photoelectric is falls under modern. So later on dia adalah some kind of argument yang the scientists keep on debating. Alright, so hopefully you guys ni lah could be differentiate. So sebab second year ni kan, second year ni is all about you should be, it's lots of equation, lots of theory and so on. So later on in the third and fourth year, you will be apply all those things and you should be able to differentiate all those things in order to apply all those equation, theories and so on. Buat kerja lebih sikit lah. Alright. So for our labs today, rasanya you guys tak ada masalah ke kan? Senyap je, all is well. So kalau ada problems, so please ask the members of the groups present. Okay. For group 3 tadi okay. Alamak. Group 3 tadi okay.
Okay.
So for the report, later on maybe saya akan create links lah for you to submit the report. Maybe via not via goals code sebab saya tak ada access to that your optics punya optics punya goals. So nanti maybe through Google links ke, or maybe through our teams punya group ni kan. So nanti saya akan share lah. You may upload all your reports here dekat kita punya group teams ni. Okay, so ada last questions about lab session kita. Tak ada, senyap dah. Semua dah pergi berbuka dah.
Everything okay tak?
Tak ada everything all is well lah kan macam biasa.
InsyaAllah.
So, last time I did to bila you should submit? A week before Raya
After Raya lah tu.
Sebelum Raya.
11 Mei.
Raya kan? Okay, so Raya is 13 May. So
11.
11 kan? Alright. So you have 2 weeks to complete all those things. So the due date for the lab reports is on 11 May. 11 May. 11 May. Is it okay with you guys?
Okay, insyaAllah.
Okay, 2 minggu kan. Alright. So saya dah bagi tahu kan the last week the outline, the lab report punya guideline and so on. Please follow our electromagnetism punya guideline. So you kena write down lah dekat our lab electromagnetism punya guideline tu we have criteria you need to be fulfilled. Let's say introduction, methodology, discussion, reference and so on. But some of you last time I did mark on your lab report dah ada dekat depan tu pun kriteria yang kena ada kat depan tu, but still dalam tu you tak buat pun. Ada yang tak tulis reference, ada yang tak buat objective and so on. So hilang markah dekat situ lah. So please follow kalau objective, methodology, introduction, theories and so on. Bukan susah pun kan, salin saja kan. So follow that one lah. Reference sama juga, at least 5, at least 5, then you will get full marks. Kalau tak, you akan dapat satu reference, satu marks lah. And then apa lagi? Tu je lah. So like previously also, lab report should be individually. So please submit it individually. Later on I will provide the links. And alright, so tu je lah. So fill up attendance for the last week. So for this week I just download it from here. So since you guys have no more question, anything nanti text dekat our Telegram group So for the other MSE 1 and 2, dia orang dah start belum tutorial ke tak ada lagi?
Tutorial
Lab
ada
dah start
lagi.
semalam. Tutorial belum.
Oh, tutorial belum. Lab dia orang dah buat jugalah.
Dah, semalam.
Semalam. Okay. Alright, okay. So kalau tak ada apa, that's it lah for today. Anything else ataupun about the tutorial and so on, please keep me updating through our Telegram group. So due date is 11 May. Jangan lupa. Okay, so kalau tak ada apa, we end our session today. Thank you for your time, and you may start writing your lab report. Okay, so thank you.
Thank you, Doctor.
Thank you,
Thank
Doctor.
you and welcome.
Thank you, Doctor.
Alright.
Selamat berjumpa, Doktor.
Awalnya.